Greetings, Dr. Dan with Optimal Optics here to introduce Unit 8P, problems about refraction of paraxial rays through a lens. I'm assuming you've already viewed the video on Unit 8. Try to do the problems yourself. If you get them all right, you can pat yourself on the back. Don't brag about it. I don't want you to make a spectacle of yourself. So this first problem talks about a biconcave lens, and we have to find the optical center. So I've labeled the vertices A1 and A2 and put the centers of curvature on the proper sides. Now remember, the radius is defined as the distance from the vertex to the center. So R1 is -10 and R2 is +16. We're also given that the thickness is 2. So we plug into our formula. And we get that the distance from the first vertex to the optical center is 0.77 centimeters. And being a positive number, it means it's to the right of the first surface. Question 2, rays of light diverging from a point 1 foot in front of a thin lens are focused 4 inches beyond it. Find the focal length. So we know that it must be a convex lens, a real object, M, forming a real image M prime. Vertex of the lens is A. Now U, remember, is a distance from A to M. It's a right to left direction, therefore it's -12 inches, and U prime is AM prime, a left to right direction, so that's a +4 inches. We'll plug into our lens formula to find F, the focal length. We'll make 12 our common denominator, and we find that F equals 3 inches. And it's measured from F to A, therefore it's on the left side of the lens. Question 3, an object is 1 foot in front of a thin convex lens of focal length 9 inches. Where is the image formed? So we'll draw our optical axis, our plus thin lens, or convex thin lens. We'll place our object M 12 inches to the left, and our focal point 9 inches to the left of the lens. So remember, U is measured from A to M. A leftward direction is a negative number, and F is measured from F to A, and that is a +9. We plug into our formula. And we move our fractions without the variable to one side of the equation. 36 is our common denominator. And we find that the image distance is a +36, therefore, measured from left to right, it would be to the right side of the lens. Question 4, an object is placed 30 centimeters in front of a thin lens. The image is virtual and 10 centimeters from the lens. Find the focal length. So this will be a concave lens because the image is formed to the right of the object, the virtual image. If the object had been placed within the focal length of a convex lens, the image would have been formed to the left, if you recall the ray tracings. So we have our signs correct. U is -30, U prime is -10. We plug into our lens formula, and we get 30 as our common denominator, and we find that F equals -15 centimeters, which means it is on the right side because it's from F to A, right to left. Question 5, the radius of the first face of a biconvex lens made of glass, index 1.5, is 20 centimeters. If the focal length of the lens is 30 centimeters, what's the radius of the second face? So I've drawn our biconvex lens with the vertices labeled A1 and A2, the centers of curvature, C1 and C2 on the appropriate sides. Remember, R1 is A1, C1, left to right, it's a +20. focal length is FA, left to right, positive 30. Air, the surrounding medium, index is 1, and the lens has an index of 1.5. Now we'll plug into our lens formula, and we'll solve for R sub 2. 1.5 minus 1 over 1 is 1/2. We'll change it into a fraction. Now we'll multiply both sides times 2. We'll bring 1/20th over to the left side of the equation. We'll choose 60 as our common denominator. There we go. And we find that R2 equals negative 60 centimeters. That's one way to write the answer. You can also write the answer that the radius is 60 centimeters and the center of curvature is on the left side, to make it clear to whoever is testing you that you understand that the center is on the left side of the surface. Question 6, the focal length of a biconvex lens is 31 centimeters and the radii of its first and second surfaces are 30 and 35 centimeters respectively. Find the index of refraction of the glass. So we'll draw our optical axis, we'll draw our biconvex lens with vertices A1, A2, and C1 and C2 on the proper sides and the focal point on the left. So R sub 1 we're given is 30, that's a positive number. A1, C1, R2 is a negative number going from A2 to C2, right to left, so it's negative 35. The surrounding index air is 1, and the focal length is 31, a positive number from the focal point to the lens. So again, it's just a matter of plugging into our formula and solving for n prime. So let's convert all these fractions to decimals. It's going to be difficult to find a common denominator. And we find that n prime equals 1.52. Question 7, the focal length of a glass lens index 3/2 in air is 5 inches. What is the focal length of the lens in water? Index equals 4/3. So our lens formula is going to be useful to answer this question. Now, 1 over R1 minus 1 over R2 is going to be the same whether the lens is in air or in water, right? The radii don't change. So we'll call that a constant K and plug in our for our variables for air and solve for K. And we find that K equals 2/5. Now we'll use that same constant for water. So now our surrounding medium has an index of 4/3, not 1. And we use 2/5 for 1 over R1 minus 1 over R2. We'll use 6 as our common denominator. And we find that 1 over F equals 1 over 20. Therefore, the focal length in water is 20 inches, a longer focal length in water compared to air. Question 8, an object is placed 8 inches from a thin convex lens. Its image is formed 24 inches on the other side. If the object were moved to a distance of 4 inches from the lens, where would the image be? So we know it's a convex lens, a real object forming a real image. So In the first case, we have that u equals negative 8 am from right to left. U prime is 24, a positive number going from left to right, am prime. We'll find the focal length by plugging in our object and image distances, using 24 as our common denominator. And we find that the focal length equals 6 inches. And now we have a new object that's at 4 inches from the lens. So our new u is minus 4 inches, and we'll solve for u prime. So we plug in what we know, and we find that u prime equals negative 12 inches from A to M prime. Question 9, a virtual image of an object 30 centimeters from a thin lens is formed on the same side of the lens at a distance of 10 centimeters from it. Find the focal length of the lens. So we know this is a concave lens because the real object forms a virtual image to the right of the object. We have u, which is equal to am, is a negative 30, and u prime, which is am prime, is a negative 10, going from right to left. And we will solve for the focal length by plugging into our lens formula. We'll choose 30 as our common denominator. And we find that the focal length equals negative 15 centimeters, meaning it's on the right side because the primary focal point's on the right side because it is measured from F to A. Question 10, a candle is 2 meters from a wall when a lens is placed between the candle and the wall at a distance of 50 centimeters from the candle. A sharp image of the candle is formed on the wall. Find the focal length of the lens and the magnification of the image. Draw our optical axis. We'll draw our wall. The wall is where the image will be formed. M is our object, and we'll place the object 2 meters or 200 centimeters from the wall. It's important that all of our units are the same, so we'll change meters to centimeters. We're given that the object is 50 centimeters from the lens, therefore the wall and the image is 150 centimeters from the lens. So u, which is am, a negative left direction is negative 50, u prime am prime, a left to right direction is a positive 150, and we will plug into our lens formula to find the focal length of the lens, which is a plus lens because a real object is forming a real image. So we'll choose 150 as our common denominator, and we find the focal length equals 37.5 centimeters. The primary focal point is to the left of the lens. Magnification, the image size over the object size, is u prime over u. We find it equals negative 3, which means that the image is 3 times the size of the object and inverted. Question 11, the distance between a real object and its real image in a thin lens is 32 inches. If the image is 3 times as large as the object, find the position and focal length of the lens. So this requires some knowledge of algebra. We're going to have 2 equations with 2 variables, and we'll use the substitution method to find what they equal. So this is a convex lens with a real object M, a real image M prime. Now notice that U and U prime have different signs, so you don't add them up to get 32, you have to subtract them to get 32. U prime is the positive value, U is the negative value. We also know that the magnification is a -3 because it is a convex lens producing an inverted image. So we find that U prime equals -3U, which we can now substitute in our first equation, and we'll solve for U, which we find equals -8. So the lens is 8 inches to the right of the object. So now we can plug in to find what the image distance is, U prime. We find that equals 24 inches. And now we can use that information to calculate the focal length by plugging into our lens formula. We find that 24 is our common denominator, and we find that the focal length equals 6 inches. And the primary focal point is located to the left of the lens. Question 12, what is the radius of the curved surface of a thin plano-convex lens made of glass of index 1.5, which forms a real image of an object placed 2 centimeters in front of the lens and magnified 3 times? So there's a plano-convex lens. Surrounding index of air is 1. N prime, the index of the lens, is 1.5. We have our object distance is -2 from lens to M. And we have the magnification is -3, again, negative because a convex lens produces an inverted image. So we can solve for U prime, and we find U prime equals 6 inches. So now that we know U prime and U, we can solve for the radius. We know that the radius of the first surface is infinity. It's a flat surface. So 1 over R1, which is 1 over infinity, will equal 0. And we are left to find R sub 2. So 6 is our common denominator. We multiply both sides by 2, and we find that R sub 2 equals -3/4 centimeters, which equals -7.5 millimeters. Or you could say that the radius of the convex surface is 7.5 millimeters, making clear that the center is on the left side. Question 13, an object is placed in front of a convex lens at a distance from it equal to 1.5 times the focal length. Find the magnification. So we'll draw our optical axis, our convex lens, our focal point, our object location. So we're given that U, which is measured from right to left, is 1.5 times the focal length measured from left to right. X is the object distance from the focal point F to M, also a leftward direction. So if you look at the diagram, U equals -1.5 F and X equals -1/2 F. So the magnification formula is Y prime over Y, image size over object size equals F over X. And we find that the magnification equals -2. That means the image is inverted. That's what the minus sign means. And twice the size of the object. Question 14, an object 5 centimeters high is placed 12 centimeters in front of a thin lens of focal length 8 centimeters. Find the position, size, and nature of the image for a convex and a concave lens. So we'll start with a convex lens. Place our focal point and our object on the left side of the lens. Real object. So we have u equals -12, a to m, right to left, negative number. Focal length measured from F to A, left to right, positive number. And we'll plug into our lens formula. And we'll use 24 as our common denominator and find that u prime equals 24 centimeters. So therefore, it's on the right side, positive number measured from left to right, am prime. Now let's calculate the magnification. Y prime over y equals u prime over u. And it's equal to -2. The object was 5 centimeters high, so the image is going to be 10 centimeters high, inverted. It's a negative number. It's a real image because it's on the right side of the lens. It's inverted. 10 centimeters high and 24 centimeters from the lens. Now we'll do the same thing for a concave lens. All the information is the same except for the focal point, okay? A concave lens has its primary focal point on the right side of the lens, and the focal length measured from F to A, going from right to left, is now a -8 and not a +8 as it was for the convex lens. We'll plug in. Isolate our variable on the left side. Use 24 as our common denominator again. And we find that u prime equals -4.8 centimeters. So it's a virtual image located on the left side of the lens. Now we'll figure out the magnification. Y prime over the object size 5 equals -4.8 divided by -12. We cross multiply, and we find that y prime equals 2 centimeters. So it's an erect image, and it's smaller than the object. So the image is virtual. On the left side of the lens, it's erect. It's 2 centimeters high, and it's 4.8 centimeters from the lens.